The fourth version of the Bernoulli's equation is called the Bernoulli's equation in a relative motion. We have, because the Bernoulli's equation is a result of the conservation of momentum, and we have accelerations in the conservation of momentum. If two different frames, for example, one of the frames is rotating in a circular motion, for example, so we have two different frames. The first one is the one which is attached to the stationary observer, and the other one is attached to the motion of the control volume or the system or the device. In such cases, we have three velocities. The absolute velocity, which is measured with respect to the fixed observer, the relative velocity, which is measured with respect to the coordinate which is attached to the moving frame, and the third one, the velocity of the moving frame itself. Similarly, we have some relative accelerations, such as the Coriolis acceleration and the centrifugal or centripetal acceleration. So, in the derivation of the standard form of the Bernoulli's equation, for example, this one, we have ignored the existence of such relative accelerations. If you include the centripetal acceleration or the centrifugal force in the procedure of derivation of the Bernoulli's equation, the final equation is the Bernoulli's equation in relative motion. This form of Bernoulli's equation is frequently used in analysis of different flow in different rotating machines, for example, pumps and compressors, especially in incompressible, because one of the main assumptions of the Bernoulli's equation is the incompressibility. So this equation, which is the Bernoulli's equation in relative motion, is frequently used in the analysis of fluid motion in incompressible machines, for example, pumps. Here we have, as I told you, we have three velocities. U is the velocity of the motion of frame. For example, in a centrifugal pump, the impeller rotates with a specific angular velocity. So U is the peripheral velocity, which is the product of the radius and the angular velocity. W is the relative velocity, which shows the motion of the fluid between blades of the impeller, between the flow passages, between the blades. If the angular velocity of rotation of the pump reduces, the magnitude of the centripetal inertia or the centripetal acceleration reduces. If the pump stops, then this term vanishes, and again the W, which is the relative velocity, will become absolute velocity. So you can replace W with absolute velocity and omit this term when we have no relative motion. So this equation reduces, in this limiting case, that equation reduces to the standard form of the Bernoulli's equation. Okay, in the fifth version, I have written the simplest form of the Bernoulli's equation. Here we have neglected the unsteadiness, the compressibility, or the relative motion, etc. And I have written the simplest standard form of the Bernoulli's equation. This form, I call this form the pressure form of the Bernoulli equation, because as you see, the dimension of each term in the equation is the dimension of pressure, or the unit of each term is the unit of pressure, which is Pascal, for example, in SI system of units. So the first term is static pressure. Static pressure because it has nothing to do with the velocity. The second term is the hydrostatic pressure, which appears in a fluid which is at rest. And the third term is the dynamic pressure. As you said, this is not pressure at all. This is a combination of the density and the velocity, but because of its dimension, which is the dimension of pressure, we call it the dynamic pressure. The name shows that it's related to the velocity, not to the pressure. Okay, the sum of the first and the third term, or the static and the dynamic pressure, is called the total pressure, or the stagnation pressure, because it's equal to the static pressure of a fluid, which its velocity becomes zero, or becomes stagnation pressure. If you omit the third term, which is true for a fluid at rest, and the velocity is equal to zero, so you can see that the pressure, static pressure, is equal to the minus hydrostatic pressure plus a constant. This is exactly the hydrostatic pressure distribution in a fluid which is at rest. The sixth version of the Bernoulli's equation is exactly similar to the fifth version, but this time I've divided both sides of the fifth form by the density, or each term in the sixth form is written per unit mass. So as you see, the dimension or the unit of each term in the sixth form is totally kinematic. And you don't see, for example, a kilogram or a Newton or something related to mass or force. And the seventh version of the Bernoulli's equation is similar to the fifth version, but this time divide both sides of the equation by the specific waves or gamma. This way, each term in the equation will become something similar to length, or the dimension of each term in the equation is the dimension of length. We call such quantities, for example, head, because this is the pressure head, this is the dynamic head, or the velocity head. And the sum of two first terms in this equation is called the stagnation head, or the total head. In different engineering applications, it's more appropriate for us to use this form of quantities. I mean the head form with the dimension of length.